Graphs of sine and cosine functions. First, we start by defining a periodic function. A periodic function is a function returning to the same value at regular intervals or periods. So in our first example, find the period of each periodic function shown below. So in this first graph, we can see that the graph just repeats over and over again. So we are looking for the period of this graph. So we want to identify, well, when does it start over again? So the general shape of one period, informally, to me, looks like a little shark fin with a tail. And then it starts to repeat over again. So I have another little shark fin with a tail. So the period itself is the horizontal distance required for the periodic function to complete one cycle, or in this case, one little shark fin with a tail. So here, the period would be 2 units, right? That horizontal distance from 0 to 2. So we can see the next one is between 2 and 4, also 2 units. So the period here is 2. For this second periodic function, I'm going to go ahead and start by looking at where the function is at the x value 0. So it's up here on the y-axis. And then I'm going to go ahead and trace the graph until I reach that same value again, where I can see it's going to start to repeat at that point. So this would be considered one period of the graph, and we want to measure that horizontal distance it took to complete that one cycle. So we started at the x value 0 here, and we come over here and finish at the x value not quite 6, so we can see that maximum point there doesn't quite line up with 6, it's a little bit past 6. And in fact, the value is 2 pi. So remember, pi is 3.14, so this is approximately 6.28. So the period here that we're going to identify is 2 pi. Let's look at the sine graph. F of x equals sine x. So this is a function. We can go ahead and substitute in different values for x into sine x and get out corresponding y values. So the types of values we can plug into the sine function are angles. So I've gone ahead and thought about plugging in my quadrantal angles into sine, and these are the respective values that we get out. And each of these corresponds to a coordinate point. So we have the graph of sine here, and let's see how it matches up with our table of values. So here we have the coordinate points labeled that correspond with each of these pairs, so 0, 0, pi over 2, 1, etc. Now, this is only highlighting 5 key points on one period of the sine graph, but the sine graph is, as you can see, periodic, and it does in fact go on forever and ever in both directions. And that we're going to refer to as its domain. The domain is the x values on which the function exists. So this says all x values in the interval from negative infinity to infinity. So this is just going to keep going on over and over again. The range is all the y values that come out of the function. So this is between -1 and 1, including -1 and 1. So the lowest y value that comes out, the smallest, is -1 down here, and the biggest y value is at +1. So notice that the sine graph passes through the origin, 0, 0, and then starts to go up. From there, identify the general wave shape of the 5 points on a period of the sine graph. So there are obviously infinitely many points on the actual graph itself, but these are the 5 key values that we want to identify: the maximum value, and the minimum value on each interval, and all of the x-intercepts. Those are those 5 key values that we want to identify on any sine graph. Now let's look at the cosine graph for the function f of x equals cosine x. So once again, we have a function. We can substitute in x values, those x values being angles. We've chosen the quadrantal angles again. And then here are our outputs, our f of x values. So after substituting 0 into cosine, cosine of 0 is 1, and so on for the remaining angles. And then again, each of these corresponds to a coordinate point on the graph that we have here for the cosine function. So let's show that matchup. So we have 0, 1, the coordinate point. We have pi over 2, 0. We have pi, -1, 3 pi over 2, 0. and then 2 pi 1. So the domain, just like the sine function, is all real numbers, so this graph is going to repeat over and over again. And the range is the same as well. From -1 to 1, those y values are going to extend. So the difference here, if you notice, the cosine graph passes through 0, 1 and starts going down. And from there, we want to identify the general wave shape of the 5 points on the cosine graph. So this cosine graph starts up here on the y-axis at 0, 1, and then starts traveling down to the x-axis, goes down to this minimum value of -1, back to the x-axis, and then back up to 1 again, where it's going to repeat forever and ever because the domain is all real numbers. Graphing transformations of sine and cosine. So let's say we're given y equals a sine bx or y equals a cosine bx. We say that the absolute value of a is called the amplitude, and on the graph represents the height of the wave. So we can see here that the amplitude is the height of the wave. So in either direction, we consider the height a positive number. That's why we take the absolute value. And the period of the graph is 2 pi over b. So that's the formula for finding the period. So that's when I have a value here in front of x, a number other than 1, and then we have 2 pi over that number. So the period formula is 2 pi over b, and that's 1 full wavelength. And if a is a negative value, then the graph reflects or flips over the x-axis. So if a is a negative value, then the whole graph is going to flip over the x-axis. Let's jump into an example. Graph 2 periods of y equals 2 sine 3x. So first we'll identify the amplitude. That's the absolute value of the number in front. So we have +2. The period is 2 pi over the value that's in front of x, so 2 pi over 3. And then we'll answer the next question, is there going to be a reflection? Well, since the number in front of sine is positive, the answer here is no. There will not be a reflection over the x-axis. So what I'm going to go ahead and do now is think about the fact that 1 full wavelength of this sine function will have to start at 0 and end over here at the end of the period 2 pi over 3. So I'm going to have 1 complete wavelength occur between 0 and 2 pi over 3. And we know that the sine function starts at the origin. So I'm going to draw a point at the origin at 0. And what we need to do from here is we need to create 4 equal parts between 0 and 2 pi over 3. So I'm going to cut it in half and then cut each of those halves in half. And we want to label each of these values. So sometimes people are just have good number sense in order to split this up, and that's absolutely fine. I'm going to give you a strategy for breaking this into 4 equal parts. I'm going to find what's called the quarter period. So the quarter period is essentially 1/4 of the period. So 1/4 of 2 pi over 3, which simplifies to 2 pi over 12 or pi over 6. So each of these subdivisions has to be of length pi over 6. So we have 1 pi over 6, 2 pi over 6, 3 pi over 6, and this last one should be 4 pi over 6. And we can see that after reducing that it is. So I'm going to go ahead and leave the rest of these unreduced for now and not really focus on that. So we know that our sine function starts at the origin, as we said, and at the next tick mark, our sine graph went up. And so it's going to go up to the height of the function, and the height of the function is the amplitude. It's going to go up to 2. So I have 1, 2 units, and I'll mark -1, -2. So at pi over 6, my function is going to go up to +2. And then my sine function turned around and went back to the x-axis. So at 2 pi over 6, at the next tick mark, I'm going to end up back at the x-axis. At the next tick mark, I'm going to be at the negative of the amplitude. So I'm going to be down here at 3 pi over 6, -2. and then I'm going to end up at the end of my period back at the origin, back where I started. If I start at 0, then I also have to end at 0. So now let's go ahead and clarify what points exactly are on my graph of 2 sine 3x. So we have the coordinate point 0, 0, so the x value is 0, the y value is 0. Up here we have the point pi over 6, 2. Then 2 pi over 6, which reduces to pi over 3, 0. 3 pi over 6, that reduces to pi over 2, and we're down at negative 2 at that value. And then finally, we end up at, as we said, 2 pi over 3, 0. We end up back at 0. So now we're going to go ahead and graph the second period. We needed 2 periods, and we're going to draw our period to the left because that's where we have space to do so. We could technically, if we had space, go to the right and draw a second period over here, but I'm going to go ahead and just work to the left. So I'm going to use all the same tick marks, but just negative. So I'm going to use negative pi over 6, negative pi over 3, negative pi over 2, and negative 2 pi over 3. And then complete my general wave shape. It should look exactly the same because it is periodic. So here is a second period of my given function. And now to answer the question about domain, the domain is all real numbers. Even though all we can see, all we've graphed, is from negative 2 pi over 3 to 2 pi over 3, the domain of any sine or cosine function is negative infinity to infinity. The range, however, is different. So now the smallest y value is negative 2, and the biggest y value is positive 2. So we'll put closed bracket negative 2 to positive 2 with another closed bracket. Let's go ahead and break down the steps for graphing one period of a sine bx or a cosine bx. So we just went through an example, and first we found the amplitude and the period. The second step was to divide the period into 4 equal subintervals and label, and this requires 5 tick marks starting at 0 on the x-axis and ending at the period. So this step was that quarter period part. Part 3, create the general wave shape using 5 clearly labeled points on the graph. Note that sine functions start at the origin with the general wave shape finding maximums and minimums at a and negative a respectively, but cosine functions start at the amplitude in general. They start at the amplitude with their general wave shape, again finding maximums and minimums at a and negative a respectively. We would then perform any reflections and make sure your graph has 5 clearly labeled points. If necessary, use a table like the one we created. Alright, let's do another example. This time graph one period of y equals 5 cosine of 2/3 x. So the amplitude is positive 5, and the period is 2 pi over, the number in front of x here is 2/3, 2 pi over 2/3. Well, that's 2 pi times the reciprocal, 3/2. So the 2's are going to cancel, and my period is 3 pi. So I'm looking at a value, well, I shouldn't put a point there, but I'm looking at starting at 0 and ending at 3 pi, and I need those 4 equal subdivisions, so I need those 5 points that are key to my graph. So I'm going to need the quarter period again. This time I'm going to abbreviate it as QP. So that's 1/4 of 3 pi, or 3 pi over 4. So each of these has a length of 3/4 of pi. So the first one I'll label as 3 pi over 4, and then 6 pi over 4 to get to the next one, 9 pi over 4, and then finally 12 pi over 4, which does simplify to our 3 pi. Now there is no reflection because the number in front of cosine is positive, so there is no reflection. So now a cosine graph starts up at the amplitude. So the amplitude is 5, so I'm just going to go ahead and label on the y-axis 5, and I'm going to put my point up at 0, 5. And then the cosine function, after starting at the amplitude, goes down to get to the next tick mark where it's on the x-axis. So I'm at 3 pi over 4, 0. And then I go all the way down to negative of the amplitude. So 6 pi over 4 is going to be over here, down here at negative 5. Then back to the x-axis. And then at 3 pi, I have to end up where I started, up at positive 5. So I've labeled my 5 key values, and now I'm going to go ahead and sketch the cosine function. So they should be curves. This should be a curve here. This bottom part should be curved. This should be curved as well. So I'm going to try to overemphasize the curve here and what the shape should look like, because it should definitely not look like a straight line. It should not look like a straight line. So I'm going to go ahead and make these a little bit thicker to really indicate that shape. So now, to really just clarify exactly what points that I know are on this one period, I'm going to fill out the table. So I have 0, 5. I have 3 pi over 4, 0. 6 pi over 4 reduces to 3 pi over 2, negative 5. Then I have 9 pi over 4, 0. And 3 pi 5. So to wrap up, domain is negative infinity to infinity for my sine or cosine functions. The range this time extends from negative 5 and goes all the way up to positive 5 for y value. So bracket negative 5 to positive 5, close bracket. Now let's graph one period of y equals negative sine of x over 4. So the amplitude here is 1. So we take the absolute value of the number in front of sine, so that would be positive 1. The period is going to be 2 pi divided by 1/4. So what's in front of the x here is technically this 1, and so I could think about this 1/4 times x. And then if I multiply by the reciprocal, I end up with a period of 8 pi. And this time there is going to be a reflection because the value in front of sine is negative. So reflection, yes, there will be a reflection. So let's go ahead and mark a value at 0. And in fact, I'm going to put a point at 0 because this is the sine function, which starts at the origin. And then over here, I will label the end of my period, so 1 full wavelength has to be completed between 0 and 8 pi. And then again, we want to split this into our 4 equal parts. Now here, I think this is probably an easy one to where we don't have to actually go through the process of finding a quarter period. So half of 8 pi is 4 pi, and between 0 and 4 pi is 2 pi. And between 4 pi and 8 pi is 6 pi. So that one's a little more straightforward, doesn't involve any fractions. And then the amplitude is 1. So here I'm going to go ahead and label 1 and negative 1. And I'm going to do this in phases actually. So I'm going to go ahead and pretend that I don't have a reflection yet. So the sine graph would start at 0, 0 and then normally go up to that amplitude value at the next tick mark. So normally would look something like this. I'm going to go ahead and fill out those 5 values, but I'm going to go ahead and draw this as a dotted function since this isn't my final answer here. It hasn't taken into account the reflection. So this is the graph of just sine of x over 4, not negative sine of x over 4. So now I'm going to go ahead and think about the idea of reflecting it. So this top part here is going to reflect and be below the x-axis. So I'll still have a point at 0, 0, but then I'll have a point at 2 pi negative 1, and I'll still have a point at 4 pi 0. So it'll look something like this. And then 6 pi will go up to positive 1, and then end up back at 8 pi 0. So this graph here, this solid graph, is the graph of negative sine of x over 4. And we'll make sure we know exactly what points we're talking about. So 0, 0, we have 2 pi negative 1, 4 pi 0, 6 pi positive 1, and 8 pi 0 as my values on the actual final graph. And then let's answer the domain and range. Well, the domain for any sine or cosine function is negative infinity to infinity, and the range, the smallest y value is negative 1, and the biggest y value is positive 1. So the range is bracket negative 1 to positive 1. Graphing translations of sine and cosine. So let's say we're given y equals a times sine or cosine of b times the quantity x plus c plus d on the outside. Now what's new, what's different about this is this value of plus c or plus d, and they each do different things. So the value that's added to x, that c is called the phase shift. If it's a minus c, then the whole graph shifts to the right. If it's a plus c, a positive c, then the whole graph shifts to the left. The value of d that's on the outside of the function, either in the back or it could be in the front, is called a vertical translation. If it's a positive d, it's going to shift the graph up. If it's a negative d, it's going to shift the whole graph down. So we can see here this minus c of a phase shift is going to shift everything to the right. If I have a vertical shift plus d, it's going to move everything up. And we still have our idea of amplitude and of period. In this example, we want to graph one period of y equals 1 plus 3 cosine of 2x minus pi. So first we'll write the general form. So we can see that it doesn't quite match up exactly. So we want to do a little bit of rewriting. We want to put the 1 in the back. We want to go ahead and add that value of d. And the inside of cosine has to be b times the quantity x minus c. So we're going to have to factor out a 2 here. And we get 3 cosine of 2 times the quantity x minus pi over 2, and then plus 1 in the back. So you can see if I distribute the 2 back in, I will get 2x minus pi. But now I can identify clearly my a, b, c, and d value. And just to be clear, don't be tempted to add these together. These do not add together. We have to follow order of operations. So let's label our amplitude, which is positive 3, the number multiplied to cosine. Period is 2 pi over 2, so 2 pi over b, so we get out just pi. And let's go ahead and identify what the quarter period is as well. So the quarter period would be 1/4 of that. 1/4 of pi is just pi over 4. The phase shift. So the phase shift is identified by this minus c value. So that's why we had to factor it out. We don't want to be tempted to say the phase shift is minus pi. That's not true. It's minus pi over 2, which means that the graph will move to the right pi over 2. There is no reflection. The number in front of cosine multiplied is positive, so reflection no. The vertical translation is going to be up 1 because I have a plus 1 on the outside. So what I'm going to do is start this in a traditional way, but then kind of stop and think about another method. So if I think about this in a traditional way, I would start by marking my 0 value, the end of my period is pi, and labeling this quarter period values pi over 4, 2 pi over 4, 3 pi over 4. And then going ahead and starting with the sketching of the graph. But the phase shift here kind of changes things for me. I'm going to have to move each and every one of my coordinate points to the right pi over 2. So I'm going to have to move 0 to the right pi over 2, pi over 4 to the right pi over 2. So that's a lot of values that I'm going to have to add pi over 2 to in order to shift everything to the right. So we can absolutely do that. We could finish this thing off and then move each of those points to the right pi over 2. But I'm going to show a different way. This next method is going to involve looking at the part that's inside of the cosine function. So I'm going to go ahead and focus on this 2x minus pi. We could also take the factored version. We could also take 2 times the quantity x minus pi over 2. It doesn't matter. We're going to take that inside part and solve the 3-part inequality. 0 is less than or equal to 2x minus pi is less than or equal to 2 pi. So we're going to take the inside only of the cosine function and put it between 0 and 2 pi and solve for x. So if I add pi to both sides, I'm going to get pi is less than or equal to 2x is less than or equal to 3 pi. And dividing each piece by 2, I get pi over 2 is less than or equal to x is less than or equal to 3 pi over 2. So what I just found was the starting value of my period and the ending value of my period. So now let's go ahead and draw our xy plane. So here we have our start of our period, pi over 2, the end of our period, pi over 2. We still do need to label the tick marks on the inside. And we did find the quarter period was pi over 4, so each of these has to go up by pi over 4 every time. So starting at pi over 2, in order to add pi over 4 to get to the next tick mark, I'm going to rewrite this with a common denominator of 4. So this is 2 pi over 4, making this first tick mark 3 pi over 4, 4 pi over 4, 5 pi over 4, and 6 pi over 4. So now I have my tick marks labeled. I'm going to go ahead and think about the amplitude of the function. Now since this is a cosine graph, my function starts at the amplitude. But remember, the start is pi over 2, not 0. So I'm going to go ahead and label 1, 2, 3, 4. 1, 2, 3, 4 downward. So I have labeled my y-axis values. And I know that I start at the amplitude, so I start at pi over 2, 3. At the next tick mark, I'm at the x-axis. At the next tick mark, I'm down at -3. I'm back at the x-axis, and then I have to end where I started, which is at +3. So this is not the final graph. I'm going to draw it as a dotted function because I haven't addressed the vertical translation. So we said that this whole graph has to move up 1 unit. So I'm going to take each one of these coordinate points and move it up 1 unit. So pi over 2, 4, 3 pi over 4 is going to shift up to 1, 4 pi over 4 is going to shift to 2, 5 pi over 4 will shift to 1, and 3 pi over 2 will shift to 4. And now I'll connect these with a solid graph. This is my final answer. It retains that general wave shape of cosine, but it is not along the y-axis because everything had to shift to the right pi over 2. So solving this inequality adjusted for the phase shift. So now you can see that because we've done kind of so much on one xy plane, the graph could look a little cluttered. So if it's not absolutely 100% clear what points are on my final graph, that's why we create a table. So on our final graph, we have pi over 2 corresponding to 4. So we have pi over 2, 4. We have 3 pi over 4, 1. 4 pi over 4, which is pi, and that's at -2. 5 pi over 4 is at 1, and 3 pi over 2 is at 4. So if I identify my domain, well, this graph does go on and on forever. We just found one period, so -infinity to infinity. But the range of my final graph is from -2 on the y-axis up to +4. So my range is -2 to +4. So let's just review those steps for graphing one period of a sine or cosine function in this form. So first we find the amplitude, the period, the phase shift, the vertical translation, and any reflections. This asterisk by the phase shift is because we want to make sure that we have this form, b times the quantity x minus c, that it's been factored to correctly identify the phase shift. And then we're going to go ahead and solve the inequality. 0 is less than or equal to the inside or the argument of the sine or cosine function. So that b times x minus c. And this could be factored like this, or it could be the original. The whole idea is we're going to stick the inside of the trig function into this three-part inequality, solve that, and the solution interval is going to give the end points of one full period of your graph. And we're going to divide this interval into 4 equal subintervals and label. So here, this step just tends to make the problem a little bit easier. Otherwise, you can just go about it where you start at the y-axis and then apply the phase shift to each and every point. But I found that it's easier to solve this inequality, recognize that the solution are the endpoints to one complete interval, and just divide up this interval. Then we create that general wave shape for sine or cosine using 5 clearly labeled points. We apply reflections, we apply vertical shifts, and we want to make sure our graph has 5 clearly labeled points. So if necessary, use a table to clearly indicate those 5 points, the x and y values. Let's go ahead and take a look at another example now. We have y equals 2 minus sine of the quantity 4x plus pi. So the first thing I'm going to do is rewrite this so it has that general form where we have sine in front, and this 2 I'm going to move it to the back so I can really think about it as that shift vertically up or down. So I'm going to start by putting negative sine, and let's do 2 things at once here. Here I'm going to factor out the 4 from each of these terms. So if I factor out a 4 from 4x, I have the x left over. Here, when I factor out 4 from pi, what's going to happen is pi is going to be divided by 4. So I'm going to have plus pi over 4, close parentheses, and then I'm going to, again, put that plus 2 in the back. So I have that general form, a sine of the quantity b times the quantity x plus c plus d. Alright, so now that I have this general form, let's go ahead and find our different parts. We have our amplitude is the absolute value of that a, that number in front of sine or cosine. So the amplitude is 1. The period is going to be 2 pi over the value of b. The value of b is in front of x, so that is 4. So 2 pi over 4 reduced down, that's pi over 2. And I'm going to go ahead and just find the quarter period right now as well. So the quarter period, so we're going to have 1/4 of pi over 2. So the quarter period is going to be pi over 8. The phase shift. So we can identify the phase shift from this form over here where I factored out the 4. So I don't want to look here. A common mistake is to say the phase shift is left pi, because of the plus pi that's right here, but in fact it's going to be left pi over 4. So since it's addition, it's going to be the opposite of what I would think. It's going to go left. So my phase shift is left pi over 4. Is there a reflection? Yes, there is. There's a negative in front of the sine or cosine function. Vertical translation, there is one. My whole graph will move up 2. And for domain and range, we can identify the domain. The domain of any sine or cosine function is all real numbers, negative infinity to infinity, but we'll go ahead and hold off on the range until we look at our final graph. So to graph this, we're just going to go ahead and graph one period of this sine function. So we're going to use the method where we go ahead and trap the inside, right, the argument, the input of the sine or cosine function between 0 and 2 pi. So we have 0 is less than or equal to 4x plus pi is less than 2 pi. And again, I can choose either version, this one here or the one that's factored out. They're equal, they're the same thing. So now here I'm going to solve for x. If I solve this 3-part inequality, I'm going to subtract pi from all 3 parts. So I have negative pi is less than or equal to 4x is less than or equal to pi. 2 pi minus pi is pi. Go ahead and divide everything by 4 here to get the x in the middle by itself. So what we have is negative pi over 4 is less than or equal to x is less than pi over 4. Scoot this up a little bit so you can see it. So we have the start of our interval and the end of our interval. So I'm going to have one period here between negative pi over 4 and pi over 4. And this is nice. It doesn't always happen this way, but this happens to be a symmetric interval about the origin. So negative pi over 4, they're the same distance away on both sides of the x-axis. So we'll go ahead and start to label our x-axis. We're going to have negative pi over 4 and pi over 4. So that's going to be the start and end of one period of my sine function here. And I want to divide it right into my 4 equal parts. And I know the quarter period is pi over 8. So halfway is nice. That's just 0. And then when I go to label these tick marks here, this is going to be positive pi over 8, and this is going to be negative pi over 8. And then we know, again, the start and the end of one of our sine functions, or one period of our sine function. Now the sine function normally starts at the origin, but everything has been shifted to the left pi over 4, so my graph is going to start over here at negative pi over 4, 0. And so I'm going to do this in phases. I'm going to go ahead and start at negative pi over 4, 0. At the next tick mark, I would be up at the amplitude. We said the amplitude was 1. Mark negative 1, so I'd be up at the amplitude. I'll be back down to the x-axis next, then negative of the amplitude, then back to the x-axis. So I'm going to go ahead and sketch this as a dotted function, because this is not the final answer. Right, so this is just sine. If I labeled exactly what this graph is, this is sine of 4x plus pi. It's only taken into account the phase shift portion and the amplitude being 1. But the negative, remember, will reflect this graph over the x-axis. So I'll switch colors to do that. So I'm going to go ahead and keep the points on the x-axis, but I'm going to reflect the other points here. So now this red dotted graph is negative sine of 4x plus pi. So it's taken into account the phase shift, and that's the sine function with an amplitude of 1 and a reflection. So the last thing that we're going to go ahead and do is apply the vertical translation. So everything is going to shift up 2 units. So let's go ahead and add a couple of extra tick marks here. Let's see, so 0, 0 will move up to 0, 2. And then my other x-axis points, let's just move those first. Negative pi over 4, 2, positive pi over 4, 2. My negative pi over 8, negative 1 will go up to negative pi over 8, positive 1. And then here I was at negative pi over 8, 1. If it goes up 2 units, it's going to go up to 3. So I have negative pi over 8, 3. And then I'm going to go ahead and connect those points together, this time with a solid line or curve, because this is the final answer. So this does represent now negative sine of 4x plus pi plus 2 with that vertical translation part. Now this is just one period, but of course it would continue on, and we know what those tick marks would be. Well, it's got a little bit ugly. They're going to move on by those quarter periods of pi over 8. So this is minus 1 pi over 8, this is minus 2 pi over 8, so we have here, this would be minus 3 pi over 8, and then we'd go down, and we have minus 4 pi over 8, and then same thing over here, it would just continue on, those tick marks would go up by pi over 8, so 1 pi over 8, 2 pi over 8, 3 pi over 8, etc. So this would go down here. And the graph is periodic, it would just continue. So we graphed, we focused on one period, right, of the sine function that was given. So now with the graph drawn, we can identify the range. The least y value is 1 and the greatest y value is 3. So our range is going to be 1 to 3, including 1 and including 3, because we hit everything in between there. And then here, we'll go ahead and fill out this table of values just to be really clear about what points are on our graph. So we have negative pi over 4, 2. We have negative pi over 8, 1. We have 0, 2. We have pi over 8, 3. And pi over 4, 2. So we have 5 distinct points on one period, clearly labeled and also written in a table. Now let's work backwards and take a look at an example where we have a graph and we're being asked to write an equation for the graph shown. So the first thing I will mention is that there are multiple possible answers for an equation that would graph this particular function. That's why it says write an equation, because it could be a sine or a cosine graph, just depending on how we look at it. So I'm going to go ahead and focus on just one period of this sine or cosine graph. So I'm going to focus on this period right here, which is starting at 0, negative 1. And I just went ahead and traced out one period where I end up down at the same location, down at negative 1 as a y value. And then from there, I'm going to go ahead and sort of extract all the information that I can. What do I see now, just focusing on that one period? So I can see that I would consider this more easily identifiable as a cosine function because it doesn't start at the origin, and I can see that the height of the wave is 1. So the height of the wave is 1, and this graph is starting at negative 1. So it is starting at the amplitude, but of course it's starting at negative of the amplitude. So I'm going to take some notes here. So I'm going to say, well, this is going to be a cosine function. And I know that its amplitude is 1, but there's going to be a reflection because the graph starts at negative of the amplitude. Now, the next thing I want to identify is, well, what's the period? How long does it take to complete one full wavelength of this cosine function? So I need to know the value of this missing tick mark that's here. I have this value marked, that's pi, but what's this tick mark here? So what I have to recognize is that what I'm being shown here is that this portion leading up to pi has 3 equal parts to it. So it's being divided into 3 equal parts all the way up until 1 pi. So when something's divided into thirds, that means that we're going to have something that looks like 1/3 pi, or pi over 3, and then 2/3 pi, because 1 would then be 3/3 pi. So this tick mark here is 2 pi over 3, so that is the period. So the period is going to be 2 pi over 3. All right, so I'll write it over here in my list, 2 pi over 3. And now my job is to write the equation for this. So in general, it's going to look like a cosine of b times x plus c plus d. Right, so I have to fill in all of my parts. So let's go ahead and get started. So the amplitude is 1, but there is a reflection. So this is going to start as a negative 1. So I'm going to put negative cosine. All right, and now the value of b. So the value of b, we're going to hold off on that for just a second. So I'm going to leave like a set of parentheses here. C would be if there's a phase shift, and we didn't identify a phase shift because we said we're starting at negative of the amplitude. So maybe I'll write that note, right? We're not identifying a phase shift. So the value of C is 0. So here what we're just looking for is this value of B. So we'll fill that in a second. And then let's talk about plus D. We also didn't recognize there to be any vertical translation. So we can see that the height of the wave is 1 going up from the x-axis and down from the x-axis. So there's no shift in that up or down at all. So that's also going to be 0. So no phase shift or vertical translation. So that makes this kind of nice because the values of C and D are both 0. So now it's just a matter of finding this value of B here. Right? So we know the period is 2 pi over 3. And we know the formula for the period is 2 pi over b. So 2 pi over 3 is our period, and then the formula for finding the period is 2 pi over b. So these have to be equal to one another. So this actually happens to be just like a really nice, easy problem because I need to know the value of b to stick in right here. Well, just look across the denominators. If I have 2 pi over 3 has to equal 2 pi over b, then 3 has to equal b. So we're just going to come down here and replace that missing value with a 3. So negative cosine 3x is an equation for the graph that is shown. Let's try one more of these examples where we write the equation for the graph shown, or write an equation for the graph shown. So here, I'm going to go ahead and start the same way. I'm going to indicate one period. So I'm going to start at some point and finish at that same height. So here I'm starting at negative pi 2, and then I'm continuing one complete wave, and it ends at 5 pi comma 2. Alright, so let's go ahead and talk about which function this looks like. So what I'm going to go ahead and do is identify this as a cosine function, but it's a cosine function that does have a shift to it. So since I'm focusing on this point up here at the negative pi 2, that's the height of the wave. So I can see that up or down, the highest and lowest that I go. In this case from the x-axis, right, it's 2 up and 2 down, so there's no vertical translation. So this is the height of the wave. So on the y-axis, I'm actually not starting at the amplitude. Looks like everything shifted to the left. So I'm going to say that this is a cosine graph, but one that was shifted to the left. So cosine, it's shifted left pi units. So normally it would start at 0, 2. But it's negative pi 2. And so we also identify the amplitude, as we said already, 2. And there's no reflection because it's up at 2. It's not down at like negative 2. There's no vertical translation, so I'll put left pi, no vertical translation. And what we're missing at this point, also no reflection, right? Said that. Little notes for myself to remember. And what's missing is the period, right? That's what we need to find and then use that to solve for the value of b. So let's go ahead and identify, well, what is the period? So from negative pi all the way to 5 pi, what's that total difference between the endpoint, the x values of the endpoints here? So total, I'd be traveling 6 pi. So over here, 0 to 5 pi, that's 5 pi units. And then this direction would be an extra pi. So total, my period here is 6 pi. All right, my period is 6 pi. So we're going to have to solve, like we did earlier, we're going to have to set the period equal to the formula for the period to solve for b. So we're going to have to set 6 pi equal to 2 pi over b. So this one is a little bit trickier, but not really. I mean, it's just solving by using cross multiplying here. So 6, or I could just think about it as multiplying by b and dividing by 6 pi, however you want to see it. So b is equal to 2 pi over 6 pi. The pi's are going to cancel. 2 over 6 reduces to 1 over 3. Alright, so I have my value of b because I identified what my period was and I set the known period equal to the formula for the period. And then we fill out our equation. So what goes first is the amplitude, and there was no reflection, so it's just 2 cosine of, what comes next is the value of b, 1/3. And there is a shift in the graph. There is a phase shift. Everything goes to the left pi. So we have to be careful. We have to include a set of parentheses here to put x plus pi. So we need those parentheses to indicate that I have a phase shift. So it has to be just with the x. If there's a number on the if there's a number for the period, a b value, it has to be on the outside. And it's a plus pi because it's going to the left, and we think it's like the opposite, right? So left we would normally think negative, but it's actually positive. And there's no vertical translation, so there's nothing I need to add, either in the back or typically for trig functions you see it in the front. So this is my equation, right? An equation for this particular graph. Now, it could have been a sine function if we wanted to think about maybe this point here is a shift from the origin to the right, like pi over 2 units it looks like, and then there would have been a reflection on the sine function because it starts going down instead of starts going up. So it just depends on how you see it, what you see when you look at this, but there's more than one way to write the equation of a sine or cosine function.